Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, Professor of Chemistry in the University of Delhi. Today, we are going to discuss about the module which will deal with high resolution electron energy loss spectroscopy, which is abbreviated as HREELS. After talking about the introduction part of this, in this module, we are going to talk about instrumentation, and this will obviously come under the paper Surface Analytical Techniques Part 1. Once we finish this module, you will be able to understand the introduction of this, then principle involved in the use of this technique. Third would be obviously what are the components which are there in this equipment and what is the schematic diagram of HREELS. When we come to introduction, in this spectroscopy, the electrons are backscattered from a sample surface where they undergo the inelastic scattering processes, and this is what we have highlighted in the earlier slides in great detail. The primary electron energies used in HREELS are quite low, so low that often it is in the range of 10 electron volts or lower for that matter. Now, low energies are chosen to achieve very high energy resolution down to or even less than 1 million electron volt at times, which renders it possible to study the electronic excitations in detail as well as about the surface vibrations. One of the most important applications of HREELS is the investigations of adsorbates on crystal surfaces with many interesting aspects ranging from fundamental surface science to applications related to certain questions, for example, in the very important areas of catalysis. Now, the principle of this spectroscopy is not very difficult to understand. Introduction of this has already been given. In general, electron energy loss spectroscopy is based on the energy losses of electrons when inelastically scattered on matter, and that's what we do in order to study this. So this energy losses of electrons when they are inelastically scattered on matter is studied, is the one which is coming under this spectroscopy. An incident beam of electrons with a known energy EI is scattered on a sample. This scattering of these electrons can excite the electronic structure of the sample. If the scattered electron loses the specific energy, that is delta E, which is needed to cause the excitation, then obviously we will study that part with the help of this. Those scattering processes are called inelastic scattering processes. The energy for this excitation is taken away from the electron's kinetic energy. Then the energies of the scattered electrons ES are measured and the energy losses can be calculated. From the measured data of such a process, an intensity versus energy loss diagram is established, which is analyzed for the purposes of surface sciences. This has been talking about high resolution electron energy loss spectrometer. Excitations of the surface structure are usually very low, energetics ranging from 10 raised to the power minus 3 electron volt to 10 electron volts. In spectra, electrons with only energy losses like also Raman scattering, the interesting feature are all located very close together and especially near to the very strong elastic scattering peak. Hence, the used spectrometers require a high resolution for getting the good quality results. Therefore, this regime of EELS is called high resolution electron energy loss spectroscopy. In this context, Resolution shall be defined as the energy difference in which two features in a spectrum are just distinguishable, divided by the mean energy of those features. That is, this could be the change in energy divided by the total energy. This would give you the measuring or measurement parameter. HREELS involves an inelastic scattering process on a surface. For those processes, the conservation of energy as well as the conservation of momentum's projection parallel to the surface hold is given by a mathematical relation, that is the EI, inelastic energy as we call it, is equal to ES plus delta E, or this is Ki is equal to Ks plus Q plus G. E are energies, K and Q are wave vectors, and G denotes a reciprocal lattice vector. Well, one should mention at this point that for non-perfect surfaces, that is, which are not very smooth, they are irregular, they are rough, G is not in any case a well-defined quantum number. Then what has to be considered when using the second relation is what we deal in this particular spectroscopy. Variables subscripted with I denote values of incident electrons, and those subscripted with S values of scattered electrons denotes parallel to the surface, and this is done with a sign of two parallel lines. Then when we come down to what are the components which are used for this, we have electron source. A device used is an electron generator. That is the one which is used to focus on the surfaces. And from here, we go to the monochromator. A monochromator is an optical device that transmits a mechanically selectable narrow band of wavelength of light or other radiations chosen for this purpose from a wide range of wavelengths available at the input stage. This talks about the two important components of the spectrometer, that is lenses and analyzers. Lenses, when we talk about, these are used for receiving the electrons generated by the electron source, and analyzer is a device that analyzes the electron or the electron source received by the lenses. This slide gives the schematic diagram of HREELS spectroscopy. Here in the initial slides, we have indicated that we are talking about the instrumentations which are involved while using high resolution electron energy loss spectroscopy. This diagram makes it very clear that what way the incident radiations come and interact with the surface and the reflected parts are analyzed. This schematic diagram of HREELS, when we conduct the experiments, is given here in the figure. The electron source is a filament tip which emits electrons with a thermal distribution of some 100 million electron volts. With the monochromator, it is possible to lower this distribution to about 3 million electron volts in modern spectrometers of about 0.5 milli electron volts. The electrons are then scattered at the sample surface. Some of them are scattered inelastically, which results in a change in their kinetic energy. And the momentum as well changes when we are measuring the kinetic energy. Possible interactions are mainly the excitations of vibrations of its orbits, vibrations of the upper layer of the substrate, that is surface phonons, and vibrations of the electrons in the substrate or in film of islands with substrate surface, or which is what is referred to as plasmons.
With the tilting analyzer, it is possible to scan the energy of the reflected electrons or reflected electrons angle resolved. Excitation with momentum parallel to the surface will lead to a change of the angle of the reflected electrons in respect to the elastically scattered electrons. The insert shows a schematic spectrum with elastically scattered electrons with an energy loss of 0 million electron volts and inelastic scattered electrons at a too small an energy or too less an energy.
The electrons are then scattered at the sample surface. Some of them are scattered inelastically, which consequences in a variation in their kinetic energy and their momentum as well when we are studying this. So possible interactions are primarily the excitations of the vibrations of adsorbate molecules obviously on the surface, vibrations of the upper layer of the substrate, that is surface phonons, and vibrations of the electrons in the substrate or in films of the substrate on the surface, of course, and this is what is referred to as plasmons. Well, moving further, with their tilting analyzer, one is able to scan the energy of the reflected electrons at any angle, and that can be resolved. Excitations with a momentum parallel to the surface will obviously guide one to a variation of the angle of reflected electrons in respect of the elastically scattered electrons. The following obviously will show a schematic spectrum with elastic scattered electrons with an energy loss of about 0 million electron volts. That means there is a practically no energy loss or very less energy loss, and in elastically scattered electrons at two stages loss of energies.
Schematic diagram of this. Here, spectrometer which is used is labeled Hreels ELS22 model with two double 127 deflectors. The drawing shows the setup and a diagram of the kinetic energy of the electrons in the different parts of spectrometer are shown. The energy in the scattering chamber E primary, which is referred to, can be varied from a few electron volts to several hundred electron volts. Higher energies are required for the measurement of excitation with a momentum parallel to the surface. The experiment is mounted in an ultra high vacuum chamber with a base pressure of about 5 into 10 raised to the power minus 11 m bar. The chamber is equipped with a sample preparation, that is what is called sputter gun, and provides an LED system to analyze the surface quality. An overporter Omicron FM3 allows to evaporate the metal films of a thickness as low as the one which is mentioned there. This could be very thin film, which could be as low as from 0.1 monolayer to several hundred nanometers. A real thin layer that can be analyzed with this. As the electrons used for HREELs are of very low energy, they do not only have a very short mean free path length in the sample material, but also under normal atmospheric conditions. Therefore, one has to set up the spectrometer in UHV conditions. The spectrometer is in general a computer simulated design that optimizes the resolution while keeping an acceptable electron flux. The electrons are generated in an electron source by heating a tungsten cathode, which is encapsulated by a negatively charged so-called repeller that prevents the stray electrons from coming into the detector unit. The monochromator is usually a concentric hemispherical analyzer. This is abbreviated as CHA. In more sensitive setups, an additional pre-monochromator is used. The task of the monochromator is to reduce the energy of the passing electrons to some electron volt due to the help of electron lenses. It further lets only those electrons pass which have the chosen initial energy. To achieve a good resolution, it is already important to have incident electrons of a well-defined energy. One normally chooses a resolution of which could be displayed or through a program it could be calculated. This means the electrons leaving the monochromator with, as example, 10 electron volts have an energy equivalent to 10 to the power minus electron volt. The beam's flux is then in the order of 10 raised to the power minus 8 to 10 raised to the power minus 10 angstroms. The radii of the CHA, as I said, CHA is concentric hemispherical analyzer. So the radii of CHA are of the order of several millimeters, and here it is up to about 10 millimeters. And the deflector electrodes have a saw-tooth profile to backscatter electrons which are reflected from the walls in order to reduce the background of electrons with a wrong EJ or ejected energy. The electrons are then focused by a lens system onto the sample. The lenses are, in contrary to those of the emitter system, are mounted and they are very flexible, as it is important to get a good focus of the sample. To enable measurements of angular distributions, all those elements are mounted on a rotating tabletop with the axis centered at the sample. Its negative change causes the electron beam to broaden. What can be prevented by charging the top and the bottom plates of the CHA deflectors will be negative. What again causes a change in the deflection angle and has to be considered when designing the experiment. In the scattering process at the sample, the electrons can lose energies from several 10 to the power minus 2 electron volts up to a few electron volts. The scattered electrons beam, which is of around 10 to the power minus 3 flux lower than the incident beam that enters the analyzer, another CHA would be there for the analyzer to carry out the experiment on. The analyzer CHA again allows only electrons of certain energy to pass through the analyzing unit. A channel electron multiplier, abbreviated as CEM, for this analyzing CHA, the same facts are valid as for the monochromator, except that the high resolution in lens system, the one that we are using, there the beam has also been broadened. To sustain a high enough electron flux to the analyzer and then to the aperture are also about a factor of 2 bigger. To make the analyzer more accurate, especially to reduce the background of the deflected scattered electrons, often two analyzers are used, or additional apertures are needed behind the analyzer, as the scattered electrons of the wrong energy normal would leave the CHA under large angles. In this way, energy losses of minus 10 to the power minus 2 electron volts to 10 electron volts can be detected with accuracy of about 10 to the power minus 2 electron volts.
Application of Hreels. Here, spectra for spotted graphene. We are discussing about spectra of spotted graphene in application of Hreels. We present a sample model for resonant feature designated as the pi plasmon in single layer graphene supported by metal substrate, which is excited via high resolution energy low spectroscopy in the of specular scattering geometry using a two-dimensional two-fluid hydrodynamic model for interband transitions of graphene, pi and sigma electron, and an empirical Drude-Lorentz model for the metal in local approximation enable us to reproduce at the qualitative and semi-quantitative levels the typical experimental features of the Hreels spectra in the visible to the ultraviolet frequency range. And second application of Hreels high resolution electron energy low spectroscopy of anion chemisorbs on electrode surface, high resolution electron energy low spectroscopy on cation exchange at benzoquinone sulfonate chemisorbed on a PD electrode. It was found that whereas the AES spectra remained invariant as the counter cation was varied from H ion to potassium to calcium ion. Profound changes occurred in the Hreels spectra, specifically the intensity of the spectral feature decreased noticeably when H ion was replaced with potassium ion, and when the potassium ions were exchanged with cesium ion, nothing but a flat line, dead spectrum was observed. Even the elastic peak was completely attenuated when the cesium ion were displaced by protons. The initial undiminished spectrum was fully restored. This outcome, while unrelated to cation exchange selectivity, is of exceptional significance in surface electron spectroscopy. It appears that the positive ions on the surface attracted the low energy incident electrons such that backscattering toward the energy analyzer was hindered, partially by potassium ion but totally by the large cesium ion. The use of Hreels to examine the molecular integrity of chemisorbed anionic species must thus take cognizance of the possibility that the counter cation chosen to preserve interfacial layer electroneutrality can have a profound effect. To circumvent such complication, low valent and small radii cation will have to be employed. In addition, although subject to instrument limitation, higher incident electron energy could be adopted. AES with incident electron energy in the kV range in impervious to the presence of counter cation. The investigation of plasmon and topical materials. The most prominent excitations of the electron gas for small momentum transfer are collectively oscillation. Quantum mechanically, these excitations are described as quasi-particle and are called plasmon. In considerations of the conduction electron as a quasi-free electron gas, the density of this electron gas is unstable toward an external electrostatic perturbation at the characteristic frequency. It means it will oscillate at this characteristic frequency like a harmonic oscillator, provided that its wavelength is longer than a characteristic cutoff, which is determined by the decay of the density oscillations into intra-band excitation.
Usually, HREELS studies, primarily electron beams here, are employed. Whenever this spectroscopy is used, the electron beams are employed with impact energies between 1 electron volt to about 20 electron volts, striking the surface at grazing incidence. EELS takes place, however, also for the swift electrons and is used in TEM studies. The energy loss is generated by the variable electric field generated by the moving electrons. Such field induce screening charges. It is this one which will induce the screening charges. On metals, the screening is perfect and the electrical field lines are therefore normal to the surface. On semiconductors, the screening is partial and the lines have a component parallel to the surface. The Fourier transform of the time dependent of the electrical field generates the frequency spectrum which extends over the frequencies up to a certain cutoff given by the electron energy. The field is just equivalent to white light in these kind of experiments. At the resonance frequencies of the substrate, absorption takes place as far as the infrared spectroscopy is concerned, on for that also and for the HREELS as well. Such energy is lost by the electrons. The electron may be reflected by the surface before or after its energy loss, and the two processes may interfere. They interfere for a range of electron volts when they are irradiated on the surface. In general, the problems that one faces while operating this kind of spectrometer. So, general problems of high resolution electron energy loss spectrometers which one faces are highlighted here. Due to the electron flux, the apertures can become negatively charged, which makes them effectively smaller for the passing electrons. This has to be considered when doing the design of the setup, as it is anyway difficult to keep different potentials of the repeller, lenses, screening elements, and the reflector. These at times can be kept constant, but has to be maintained in a very proper manner. Unstable potentials on lenses or CHA deflectors would cause fluctuations in the measured signal. Similar problems are caused by external electrical or magnetic fields in the form of a kind of noise which is recorded in the spectrometer. Either they cause fluctuation in the signal or add a constant offset in this. That is why the sample is normally shielded by equipotential metal electrodes to keep the region of sample field free, so that neither the probe electrons nor the sample is affected by external electric fields. Further, a cylinder of a material with a high magnetic permeability, example Mu metal, that's the target, built around the whole spectrometer to keep magnetic field or field inhomogeneities at the experiment down to 10 mg or 1 mg per centimeter. Because of the same reason, the whole experiment, except the lenses, which are normally made up of coated copper, is designed in stainless anti-magnetic steel, and insulating parts are avoided wherever possible. So students, having talked about the introduction, then having come over to the stage which deals with the instrumentation, we can now very conveniently summarize about what you have learned in this module. Since it is dealing with instrumentation, I'm sure you would have picked it up very easily, as the electrons used for HREELS spectroscopy are of low energy. They do not have a very short mean free path length in the sample materials, but also have under normal atmospheric conditions. Therefore, one has to set up the spectrometer in UHV, that is ultra high vacuum stage. The spectrometer is in general a computer simulated design that optimizes the resolution while keeping an acceptable electron flux, which is automatically done. The energy for this excitation is taken away from the electron's kinetic energy. Then the energy of the scattered electron EAs are measured and the energy loss can be calculated. As the incident electron in this model has to be scattered in the region above the surface, it does not come to a direct impact at the surface. And as the amount of momentum goes on, it is transferred and is therefore small in terms of scattering. And this scattering is of a very much, this goes on very much onto the specular direction, the direction in which the scattering takes place. Well, continuing the summary of this particular part, we have excitations of the surface structure as usually very low energetic values ranging from 10 raised to the power minus 3 electron volts to about 10 electron volts. In spectra electrons with only small energy losses, like also Raman scattering, the interesting features are all located very close together and are especially near to the very strong elastic scattering peak. Hence, the used spectrometers require a high resolution. So this, once the high resolution is there, that electron deflection can be analyzed subsequently. Thank you very much.